Hi, this video we will be looking at application of entropy change of ideal gas. And in the previous video, we talking about these three important equations to solve entropy change for ideal gas. One is through two formulas are from method number one, which is approximate analysis, assuming specific heat is constant. The second one is assuming a specific heat indeed changes with the temperature. We have only one equation. And here we are having this example to solidify that concept we learned. Okay, so air. Well, that gives us a clue that's ideal gas. It's compressed from initial state, so given here, whoops. Our initial state P1 is 100 kilopascal, and the temperature T1 is 17 degrees Celsius, and the final state P2 is 600 kilopascal, and the temperature T2 is 15.7 degrees Celsius. And we need to find the entropy change delta S. Okay, well, this is for sure the entropy change of ideal gas, right? Because when you are taking on a problem, I think the very important thing is to figure out, to recognize this problem. And right now, we'll just look at this one topic at a time. Then we know it belongs to figuring out ideal gas entropy change. But when you are having a mix of so many problems, you want to identify it. That's a very critical step there. So here, trying to find the delta S for ideal gas. And we're talking about method number one, which is using our assume CV and CP to be a constant value, right? That does not change. And so with that, we come up with two equations there. And remember, we mentioned about which one to use, but really depends on the problem. So for example, here, I'm actually going to write it down really quick so you would make a determination right here on the spot on which one to use. Then you will know in the future which one will be to be used for that particular situation. I think I have down wrong here. I didn't write down the correct one. So S2 minus S1 is CV average natural log T2 over T1, right? And here it's going to be CP average natural log of T2 over T1. But here we're going to have minus R natural log P2 over P1. Okay, those two equations are for method number one. We're using the average specific heat. Okay, assume that's a constant. But let's look at this one. Which one will be better? Because we know T1 and T2 and P1 and P2, so obviously this is a winner, right? Okay, so we go with that one. S2 minus S1 is going to be CP average. So what would be the average temperature? Right? So T average will be T1 plus T2. That will give us about 74 degrees divided by 2, so that's 37 degrees Celsius. And 37 degrees Celsius, that's 300 Kelvin. And what substance is this? It's air. So we're going to table A to B. If we look at table A to B, is actually have, or A, right? A is basically 300 degrees, but let's just say here 300 degrees Celsius. Our CP value is 1.005. So knowing that, we can write down the value, natural log T2. Here, I cannot use 57. I have to use absolute temperature. So be careful with that term. And T1 will be 17, and this have to be adding to 73 as well. Now R, what's the R for the air? 0.287, right? That's from table A1. And the natural log P2 over P1, that's 600 kilopascal over 100 kilopascal. Then we can calculate, put all those values in there. We will have about negative 0.3842, and the unit for entropy, specific entropy change, is kilojoule per kilogram per Kelvin. That's our answer for delta S. Okay, now we can look at method number 2 using exact number from table A17. So using the property value from the air table. So method number 2, our equation will only have one, which is S2 minus S1 equals S0 T2 minus S0 T1 minus R natural log P2 over P1. Okay, first time using that table for this purpose. So let's go take a look. We're going to table A17. And we have two temperature, right? First temperature is T1. T1 is 17 degrees Celsius. So T1 here is 17 degrees Celsius. That will give us about 290 Kelvin. And the T2 is 57 degrees Celsius. Then we plus 273. That will give us 330 Kelvin, right? So those are the two temperature. Now let's see. At table A17, do we have S0 column? Right, we do. And at 290, it's right here. And S0 is equal to 1.0. Oh, that's actually 290. I'm going to go find the 330 first. At 330, S0 is 1.79783. And at 290, and here is that value, minus 1.66802. Here we go. Now we have those value. We're going to minus R is 0.287, and natural log of P2. P2 for this value, this problem is 600, and P1 is 100 kilopascal. So we cancel them out. Kilopascal, kilopascal cancel out, and we go ahead, calculate this, and we would get the answer of negative 0.3844 kilojoule per kilogram per Kelvin. And that's our delta S using tabulated data for ideal gas table. Which one is more accurate compared to these two methods? This one is more accurate, right? Because this one we estimated using the average temperature specific heat to do it. So that is the end of this example, how we calculate entropy change of ideal gas. Okay, so that will be it. I'll see you guys next time. Bye now.